What is up, everyone? Welcome back to my channel, InfoSec Lab, and it's another day of TryHackMe Advanced of Cyber 2024. In today's room 20, day 22, we're going to learn about Kubernetes and DFIR, which is digital forensic and incident response. We're going to learn about Kubernetes, what it is, and why it is used. Also, we learn about DFIR and the challenges that come with DFIR in an ephemeral environment. And we also, last but not least, we learn about DFIR and how it can be done in a Kubernetes environment using log analysis. All right, for those of you who might not know, Kubernetes is a very common popular technology that's been adapted by many companies to orchestrate containers. We will dive deep into those definitions shortly. All right. Kubernetes, it is a word. Back in the day, it is very common for companies and organizations to use monolithic architecture when building the applications. So a monolithic architecture is that the entire application is built in a single code base. Everything is in the same code base, from authentication to authorizations and then to functions, everything. And because of that, the downside of a monolithic application is that when you have a certain part of the application that you need to scale up, you have to scale up the whole application. So let's say you only need to let's say Netflix, for example, if they only want to scale up the streaming functions or streaming service of the websites, then they have to scale up the entire website, which is inconvenient because they have to scale up other services like billing, registrations, or subscriptions, etc. Right, so that's where the microservices architecture come in. Microservices is on the other hand are the architecture in which an application is built on multiple mini services called microservices. These microservices are responsible for different parts of the application. So again, using Netflix as an example, you have streaming service, you have registration service, you have subscription service, and billing service, etc. Right? Let's say that you have a lot of movies coming out for this holiday seasons, and you need to scale up the streaming service. Then, by using the microservice, you only need to scale up the microservice of the streaming services. You don't have to scale up the whole applications with other services. So that's the difference between monolithic architecture and microservices architecture. And because of its convenience, a lot of companies have started to adapt this microservice architectures to make it more convenient. These microservices are run in containers, and in a large-scale application, it is kind of hard for developers and for the team to actually manage those containers. This is where the Kubernetes come into place. So Kubernetes is a container orchestrating system. So Kubernetes is a container orchestration system. Imagine one of those microservices mentioned earlier is running in a container, and suddenly there's an increase in traffic, and this one container can no longer handle all requests. The solution is to have another container spawner for this microservice and balance the traffic between the two. Kubernetes takes care of the solution, orchestrating those containers when needed. So let's say, for example, Christmas is coming, right? And suddenly there's an increased amount of people watching Netflix. So now Netflix has to scale up their streaming services, like having more containers spun up, right? But after Christmas, after the holidays, the number of people watching Netflix go down. What now? Instead of manually queue those containers, that Kubernetes will automatically spin down those containers because they will no longer be needed to scale up the streaming service. So all right, so when it comes to Kubernetes, we need to learn a few terms in Kubernetes. Pods. In Kubernetes, containers run in pods. These pods run on nodes, and a collection of nodes made up a Kubernetes cluster. It is within the cluster that Masquidi and code investigation will occur today. Okay, so today we're going to be investigating an incident in a Kubernetes environment and performing a digital forensics and incident response. Moving on to the next concept, DFIR, or also known as digital forensic and incident response. These two investigative branches of cybersecurity comes into play during a cybersecurity incident. A DFIR expert will likely to be called action as soon as an incident is ascertained and be expected to be perform an action that fall into one or both of these two disciplines. Digital forensics is like any other forensics discipline, aimed to collect and analyze digital evidence of an incident. The artifacts collected from the affected system are used to trace the chain of attack and uncover all facts that ultimately led to the incident. TFIR experts sometimes use the term post-mortem to indicate that the analysis starts after the incident has occurred and is performed on an already compromised system or network. Incident response, on the other hand, is why similar to digital forensics that in terms of analyzing the logs and evidence, it focuses more on the responsive side, meaning that it will analyze the incidents and then try to it means that an incident response analyst will try to analyze the data, the log, and try to come up with the solutions to mitigate the current threat and fix the holes, fix the bugs, and then after that try to recover the system to its regular state and improve their security postures. So in the incident responder will isolate infected machines, use the data collected during the analysis to identify the hole in the infrastructure, security, and close it, and then recover the affected system to a clean previous to compromised states. Okay, so TryHackMe has provided us with a very clear analogy for the digital forensics and incident response. Picture the incident response as an emergency first responder whose aim is to contain the damage, extinguish the fire, and find and stabilize all victims. On the other hand, the digital forensics analyst is the crime scene investigator or detective trying to recreate the crime scene and ultimately find evidence to identify and frame the criminal. Okay, so that's the basic difference between digital forensics and incident response, but a lot of times these two branches of cyber investigations go together. Okay, moving on to the next excruciatingly ephemeral. So the problem with digital forensics, DFIR, is that in Kubernetes environment, because the containers, because a lot of containers are only spun for a short period of time, it is hard to collect all the logs to such containers. And sometimes when an incident happens, we may not have enough log stored in the database in Kubernetes or on the system to actually analyze the incidents. That's the issues that we have right now. So what can we do about that? It just means that we have to expand our digital detectives toolkit. The key is to keep track of the ongoing in your often ephemeral workloads within your Kubernetes environment. So in other words, we have to try to increase the visibilities, i.e. integrating more log system into the Kubernetes environments and the containers environments. There are a few ways we can do this. One way is by enabling Kubernetes audit logging, a function that Kubernetes provides, allowing for requests to the API to be captured at various stages. For example, if a user makes a request to delete a pod, this request can be captured and why the pod will be deleted and logs contained within it lost. The request made to delete it will be persisted in the audit logs. What requests events are captured on the can be defined with the audit log policy. We can use these audit logs to answer the questions what helps us in security or DFIR contexts, such as What happened? When did it happen? Who initiated it? To what did it happen? Where was it observed? From where it was initiated, or to where was it going? Of course, this is just a few basic ideas that scratches the surface in terms of the level of visibility that we can achieve in Kubernetes environment. We can feed these audit logs as well as events from other security relevant sources into a runtime security tools. Now, in this, now we can think of ELK, or we can also think of Splunk, those SIM tools where that collect log data events into one centralized hub to extract and analyze the events. Okay, let's move on to the activity in the room. Now this is a little bit complex and in terms of the technical and then the concept, so I'm just going to read through and follow along because I'm not very familiar with Kubernetes. I only know some basics of it, so just like many of you, I'm just like a beginner, and so I'm going to go through the exercise step by step. Alright, let's start our investigations. As mentioned before, some of the log sources will disappear as the sources like pods are ephemeral. Let's see this action in first. Open the VM, open a terminal and start K8 using the following command. So mini kube start. It will take roughly 3 minutes for the cluster to configure itself and start. You can verify the cluster is up and running using the following commands. So this is another command we can use: Kubernetes kubectl get pods. Alright, so this is going to be a command to verify that all the clusters are configured. If all of the pods are up and running based on the status, you are ready to go. This will take another 2 minutes. Since we know that the web applications was compromised, let's connect to that pod and see if we can recover from any logs. Connect to that pod using the following command. So this command kubectl get pods -n web view will list all the cluster running on the current Kubernetes environment. And then this command kubernetes exec -n review naughty or dice is, I assume this is going to be the part that the application was run on. So, and then once you connect to the container of this application, you open a terminal and run a bash terminal. Okay, while waiting for the cluster to be configured, let's continue with the reading and we can come back later. Once connected, let's review the Apache 2 access log. So now we're on the Linux, we're on Unix Ubuntu container. We can use this command cat log Apache access log regular directory. Sadly, we only see logs from the 28th October when our attack occurred later on. Looking at the last log, however, we do see something interesting with a few requests being made to a shelley.php file. Where is it? Can we still? Okay. The cluster has been configured. So kubectl get pods.n where view. Okay, so the pods have been configured, but the status are still error, meaning that they're not ready to use. So let's wait for a few more seconds. Going back to the reading. Sadly, we only see the logs from the October 28th when our attack occurred on later on. Looking at the last log, however, we do see something interesting with requests being made to a shelley.php file. So this tells us that we're on the right track. Terminate your session to the pod using exit. Fortunately, my security knew that the log source was ephemeral and decided to ensure that remote backups of the log source were made. Navigate to your backups directory. Okay, this one we don't have to wait for the container. Open a new terminal. Okay, this is running. So cd over here. Okay, cd gfir. Okay, we have the audit log. We have the docker registry logs.log, and then we have pod underscore apache access log. Okay. Navigate to our backup directory using this command, where you will find the access log stored in the pod apache access log. Alright, let's cat this one. Okay, review this log to see what the malware is up to. You know what? Let's just maximize it. Open a new tab. It's going to be easier. So we have get request, user agent. So have this IP address. I would assume from the source IP address. We see some request, submit request right here. This is user agent. The date, timestamp, get request, style. All right, here. Looks like on the local machine trying to get a request Shelly Pi with a command who am I. This is a shell on the target machine that execute. This is remote code execution. Okay, this who am I command ls cat db.php who am I which and cat. Okay. Okay, review the logs to see what my malware was up to on the website and answer the first 3 questions at the bottom of the task. Okay, let's scroll down and see what the questions are. Right. Which is the name of the web shell that was used by my malware? Right here, shelly.php. Shelly.php. What file did my malware read from the pod? It's db.php. Okay, and then what tool did my malware search for that could be used to create remote? Oh, netcat nc right here. The which command looking for the locations of the specific the specified name. In this case, is netcat. What IP connected to the Docker registry that was unexpected? I think it's for the next part. Okay, yeah, the first 3 questions. Okay, let's go back to the pods and see if they're still running. They're all running. Okay, I've got this one. Image pull back off. Not sure what that means. Kubed. So the image pull backup error is a common error message in Kubernetes that occurs when a container running in a pod fails to pull the required image from a container registry. This error can occur for a variety of reasons, including network connectivity issues, incorrect image tag or name, missing credentials, or insufficient permissions. Okay. Then how do we fix it? Do we just wait for it to run again? Funny, this is the name of the container that we have to run. Or not? No, it doesn't have to. Okay, so there's something wrong with my VM machine, my virtual environment, so I can't really get access to this pod container. But based on the exercise right here, except for this one naughty nor nice image or container, the rest is running as expected. So over here, we only see that, it's been explained that we only see the logs from the 28th of October when our attack occurred on later on. Looking at the last log, however, we do see something interesting with a request made to the Shelley pod, which is this one on this screenshot right here. Okay. And then this log is also logged in this file right here, the pods apache.log right here. So yeah, in this case, I don't really need to access this specific container, so I should be fine for now. Hopefully I don't have to use it later. Okay, continue. Sadly, our investigation hits a bit of the brick wall here. Firstly, because the pod was configured using a port forward, we couldn't see the actual IP address was used to connect to the instance. Also, we still don't fully understand how the web shell found its way into the pod. However, we rebooted the cluster and the web shell was present, meaning it must live within the actual image of the pod itself. That means that we need to investigate the Docker image registry itself. To view the registry container, run the following command. So docker ps we'll have the first image registry right here, and then second one is this one. Okay, now let's connect to the instance to see if we have any logs. Which instance? Oh, I guess it would be this one. Docker container name. Okay, just like you. Okay, this is a little bit hard to read, so let me try to view in full screen. Hopefully it helps. Yep, much better. The name is registry private right here. It's the very last columns right here. Okay, exact, and then registry private. Docker exact container name registry /id. Oh, either one. Okay, ls dash la varlog. Okay, ls dash la varlog. Nothing. There's nothing. So basically what this command does is it goes into the very first container, it goes into this container right here, and then try to see if there's anything in there, but there's nothing. Again, we hit the wall since we don't have any registry locks. Luckily, Docker itself would keep a locks for us. Let's pull these locks using the following command. Okay, Docker locks and then container. Docker lock and then container. Now earlier I was using the container name. Now I can use the container ID, and then if you think that the ID is long and hard to remember, copy paste. One trick is you can actually use the first 5 characters of the container ID, and you should be able to do it. So in this case, C398E, C398E, and it should well, okay. So we see all the logs here, which is a lot. Moving on. We have hit the wall. Okay. So now we run this command and the logs are populated. Now we have something we can use. These logs have been pulled out from you and are stored in the home. Okay. So again, if any of you have any issues with the containers up running, you can actually view the logs right here in Docker registry logs. Same thing. Same thing. Okay, now we have something we can use. These logs have been pulled for you in this directory. Let's start by seeing all the different connections that we made to the registry by searching for the head HTTP request code and restricting it down to only the first item, the first IP. Alright. So which one easier? Let's use this one because we already have the log right here. Cat Docker and then thread head. Now we have filtered everything on head, and we're going to use the cut command to only filter out the first field, which is the IP address right here. We're looking for the IP address. Cut. Alright, so we have 2 IP addresses, 172.17.0.1 and the other one is 10.10.130.253. Okay, we got some findings. One 72.17.0.1 and then 10.10.130.253 with that 2 IP address. Cool. What's next? Here we can see, okay, connections. However, we can see the connections were also made by this IP address. Let's find all the requests made by this IP address. Run this one and then 253, yes. No, not this one. Okay, not too bad. We see a for one. We see some patch. Okay. option action right here. Some 404. We see some post action right here. Interesting. Okay, let's move back. Now we're getting somewhere. If we review the first few requests, we can see that several authentication attempts were made. Yes, those 4-1 right here. But we can also see that the request to read the manifest, the wishlist web image succeeded, as the HTTP started call is to return this log. So image, we have image. Which one though? Get wishlist. Okay, latest. Oh, so this is the log entry that requests to read the manifest for the wishlist web image. This is the request that was mentioned right here. Okay, this is a suspicious one. Okay, so now what we also notice is the user agent in the request is Docker, meaning this was a request made through the Docker CLI pulled from the Docker CLI to pull the image. This is confirmed as we see several requests to download the image. From this we learn several things. Okay, let's okay. From this we learn several things. The Docker CLI application was used to connect to the registry. Connections came from 10.10.130.253, which is unexpected since we only upload images from 172.17.0.1. So this IP address is a suspicious IP address. If they had access to the credentials pool on image, the same credentials might have to allow them to also push a new image. We can verify this narrowing our search to any patch HTTP methods. The patch method is used to update Docker image in a registry. So yes, we saw that patch request. Okay, where's the mouse cursor? It was towards at the bottom right here. This one. Or you can just filter it out. Nope. Let's just use this one and then grab. Yep, we all see. This is the request to update the image registry. Okay, this is not good. It means that malware could push a new version of our image. This would explain how the web shell made its way into the image. Since malware pulled an image, made malicious updates, and then pushed this compromised image back to the registry. Use the information to answer the questions 4 to 6 at the bottom of the task. Now that we know malware has access to the credentials of the Docker registry, we need to learn how he could have gained access to them. We use these credentials in our Kubernetes cluster to read the image from the registry. So let's see what could have happened to disclose them. Alright, before we move it on, let's try answering the question from 4 to 6. What was the unexpected IP address? This one. 10.10.132.50. What time is the first connection made to IP address Docker registry? We have to do it again. Okay, what time is the updated malicious image pushed to the registry? We have two events right here. Which one? Let's pick this one, even though they don't really matter too much. Oh. So if it's not 31, then it's 28. What time is the image updated malicious pushed to the registry? What? Okay, if it's not, okay. Let's try it again, slowly. Let's try this one first. What time is the first connection made from this IP address to the Docker registry? What's this one? Hold on, let me double check. Yep. There's no way. Okay. Oh, so the format of the answer screwed me up. So if it wasn't 31, then it should be 28. Okay. What is the value stored in the pool grants secret? Okay, this one we have gone over. So let's go back. Where were we? We were right here. Answering the question 4 through 6 at the bottom. Now we know that Myanmar will have access credentials of the Docker registry. We need to learn how he could have gain access to them, and we use this as we use these credentials in our Kubernetes cluster to read the image from the registry. Alright, so looks like the attack happened via an authenticated Docker registry push. Now it's time to return to Kubernetes environment and determine how this was possible. Okay, Maxcader was made aware that malware was given user access to the naughty on nice. We have to run this one again. What was the command? Hopefully it was up and running. No, it's not. What happened if I try to run this command? I don't think it works. Mini kube help to help restart option. Start this and pause. Dashboard. I'm not sure what happened if we run this command again. Does it fix the error? Let's try that. Oh no, not this one. Mini kube start. Hopefully this time it works. Alright, in the meantime, let's go back to the reading and then see what happens next. What was it? Access credential pulled in. Okay, we were. Nope. Mosquito was made aware that malware was given user access to the naughty or nice Kubernetes environment, but was assured by the DevSecOps teams that he wouldn't have sufficient permissions to view secrets extractor. The first thing we should do is to make sure this is the case. To do this, Mosquito decided to check what role was assigned to the mayor. Okay. kubectl get role bindings where view. We have job running binding and a mayor user binding. Once we get the user binding, kubectl describe role binding. Mayor user binding and where view. Automation the current role. Doesn't tell me anything. We have a role called mayor user. Okay, so this is the role created. Let's try. kubectl describe role mayor user in where view. Scuba. And we got parts exact execution. We have role binding authorizations and we have role arbeit authorizations. We have parts. The output here tells Mosquito something very important. A lot of permissions listed here are as you would expect for a non-admin user in Kubernetes environment. All of those except for the permission to parts execution. So these are normal. This is the one that's not normal. Yeah, this is why my malware could go into the image registry, make some changes, and then update or push the change. exec allows the user to shell into the containers running within the pod. This gives Mosquito an idea that what Mayor may have done. To confirm her suspicion, she checks the audit log on Mayor malware's activities. Okay, cat lock dot lock grep color equals always, and then we have a long string which I'm not going to type out. Just copy and paste. It's got one at the end too. So basically, this returns a lot of logs, and see. Let's go through them as must get start from the attack path taken by the malware. Okay, we're going to use this command cat audit. Okay. This log snippet tells us that malware attempted to get the secret store on the cluster but received 403 response as he didn't have sufficient permission to do so. Okay. This is where the log starts. Object reference secrets. Okay, the resource is secret. The verb is list. Okay, try to list the secret. Resource username malware. Okay. And what was the response? This is the IP address, the source IP address. Something new. Copy it down. Cat event audit log right here. Request URL. User agent. This is user agent. Timestamp. Okay. And this one. Oh, we got some forbidden. The 403. Yes. Okay, so these are the logs events that were mentioned in this sentence. So basically, malware was attempting to get the secret store on the cluster, and now by using this command, we can see that he also tried to get the role present on the cluster. Yep. After being denied secret access, malware then started snooping to see what roles were present on the cluster. Okay, let's see that. Verb using the resource. Well, to be honest, these are a little bit hard to read and digest. Wait, let's see. After being denied secret access, may start snoop around to see what roles are present on the cluster. Resource malware right here. I'm just so confused. Object resource secrets. Wait, is it the same command? Grab class of a user. Yeah, it's the same. No. Get row. Okay. Let's move on. I mean, brr. Once running the previous get row command, maybe we have found a row named job runner. We found that, okay. This logs tells us that Mayamawa then described this row, which would given him the pieces information about. Regarding the row, most important is our investigation would have told him the row has secret read access. So respond right here. This is forbidden. Example system of it. Interesting. Resource paths namespace will response status in the code. Respond complete URI the GET request. Groups example system authenticate source IP user agent resource paths namespace web view. I'm not sure. Let's take a look at kite event. Describe the rows. So after running this command, you should be looking at this. Okay. Audit K level metadata, audit ID, stage, response complete. Get user, okay, username malware, groups, example system authenticated, source IP. Alright, so I found it, but it's just like I don't get the log. Oh, like there's so much information to digest right now. Okay, let's just move on for now. Once running the previous command, Mayamawa will have found the role named job runner. These logs tells us that Mayamawa then described this role, which would have given him the pieces information regarding the role. Most importantly, for our investigation, it would have told him this role has secret read access. Okay, so from this one, no. Oh. So this is where my malware was trying to describe the role. This is the API calls right here. And then here the user performing this this API request is my malware. Okay, from this source IP address on. Oh, so now it makes sense. And the name, and over here it specify the resource being requested is roles, the namespace value, the name of the role is job runner. Okay, so this is the log that shows, basically this is the log that shows malware was trying to get information about the job runner role. Okay, moving on. Cat audit, get role bindings. Oh, by the way, I have to extend the machine. Now knowing the role can build secrets, Mayama will try to find its role binding to see what was using this role. Okay. Cat audit, username mail grab resource. Wait, how are these two commands different? Okay, I'm confused. I'm so confused. Okay, was running previous role command. Okay. Get role bindings. Now knowing the role can be circuit, Mayama was trying to find the role binding that was suitable. Okay, let's see. Where's secret? Let's try running this one. Now it's easy. Kind event API request response complete. Okay, I'll try. Okay, so this is from the malware roles, right? Get role bindings, paste. Let's see if we can find anything. Response request URL value limit. Okay. So this is the error saying that your malware doesn't have any permission to view the secrets. But the thing is, I'm so confused on these terminals. Okay, think I get it now. So basically, I thought these are using different commands, but basically they were just using the same command. It's just different locations where to look at. If I believe, yes. Yeah, this is where I was a little bit confused, like, why are these commands look the same? Because I thought that, when describing the role or just getting the role bindings or describing the role binding, we use different kind of commands. That's where it was confusing to me, but now I get it. We ran this command, and then to get the role bindings we look at different places. To get the describe the role binding we look at different places within the log itself. Okay, now I get it. Okay, get paths, the same thing. It's going to be right here. Username group get paths. Here we can see malware now armed with the knowledge that a service account has a permission. He needs list on the paths running in the web view namespace with Kubernetes get paths command. Okay. Path morality checker. Malware described the path as morality checker. He then would have found out that this path runs with a job runners as a service account attached, meaning that if he were able to gain access to this path, he would be able to gain access in the read access. So we made a morality get here, and then resource path namespace web view name morality response status code 200 timestamp annotation authorizations decisions allow. Okay, allow role binding user. Okay. As mentioned in the role discussion, exact is a permission usually not included in non-admin role. It is this exact reason that this case, Maxgiddy feels confident that DevSecOps team had overly permissive role-based access control in place of the Kubernetes environment, and it was this that allowed malware to run exact command as captured by the logs above. This one. And gain shelf access to morality checker. Confirm her suspicion for the Maxgiddy run a follow command to retrieve audit logs from the current job runner service. Okay, here we can see a few commands being run. You see malware is being able to run get command on the circuits list them. But most importantly, we can see he has indeed been able to escalate his privilege and get access to the pool grants secret using the job runners as a service account. So where was it? Response object right here. Right, Kubernetes create update. Still show nothing. Kubernetes resource secret namespace webview name. The name is pool creds right here. Okay. API version. Response is 200. Okay, the final piece of the puzzle resolved around this secret. Finally, she runs a command and the attack path is confirmed. kubectl get secret pool creds and webview.o. JSON path equals dot data dot to config JSON base support equal and we found the password McNaughty. What is the value stored in the pool credit secrets? Is it the whole thing? Yup. And we finished with the room. So again, this is a little bit confusing for me, and I'm pretty sure that it happens to a lot of you guys too. But I mean, eventually, as I spent about 10 or 15 minutes working on the logs, I kind of understand what happens. So the way it's confusing because there's so many information to digest. Let me try again. Let me try my best to explain. So as you can see that I just run this command kubernetes get secret pool creds and then that -n webview and -o and then output in a JSON format, right? Maybe a malware actually did something similar to that one, but maybe he didn't output a JSON format, but it doesn't matter at this point. What I'm trying to say is that when you run this command, this kubectl command right here, it will be logged into the other log right here, and then this is what it should be displaying. So when you perform the get secret pools, a certain API call is made right here. Get is the action right here, and then secret pools is right here. It's the resource that the action is being acted on. And it also specify the user is the system service account webview job runner SA. So the whole thing is a little bit confusing because I wasn't familiar with how the log works or how Kubernetes log all the events, and apparently the more I dig into that, I kind of understand. Okay, when you perform this command like CLI kubectl get secret pools, then an API is called in the backend, and this is the URL of that API right here. The request URL right here. So yeah, pretty much that's it. The same similar to the above outputs. This is the request URI, and then the paths right here. This is the command. I believe the command he ran here on the front end should be something like what we had at the beginning, which is, I don't remember. I believe it was this one. Or something else. Something. Okay, let's go to the get parts part right here. So when you perform this Kubernetes CLI, kubectl get parts -n value, then in the backend in the log it shows that an API call is being requested right here, and then you list everything. The user who performed this action is malware, and then the source IP address where this action is being performed, from where the API is called, and everything, the response, the request timestamp, the stage timestamp, and etc. And then if there's any additional error messages printed out, then it will show right here authorizations or whatever it is. So yeah, it's confusing. It may cause headache for some of you guys, but if you're really interested into DFIR and Kubernetes, then this is a good room to actually dive deep into and study more about this. For me, I'm not a fan of this, but this is a good learning experience and it's a fun room to work on. So thank you very much for watching my video, and then I know it's kind of long and then tedious, but hopefully you enjoyed that, and then hopefully that if some of you struggle, then you can see me struggle too. That's the point of making of these videos. And so that's it for today, and I'll see you next time. See you. Bye.